In Volume 1 of this series, we learned how 4-cycle and 2-cycle engines work. We also looked at lubrication and cooling systems. In this volume, we'll take a look at systems that supply fuel to the engine and how the power generated by the engine is transmitted to the drive wheels. An engine requires both fuel and air in order to run. The carburetor mixes the fuel and air together so that they burn easily, and then feeds this mixture to the combustion chamber of the engine. The carburetor does this by mixing the fuel with air so that it can easily be atomized. It also mixes the fuel and the air in the optimum proportions for the engine to run, and determines how much of the fuel-air mixture the engine requires in order to run. Using this atomizing principle, the carburetor takes the fuel and turns it into a spray. Let's take a closer look at how it does this. When air is sent to one end of the horizontal tube, the pressure at the bottom of the tube in the water drops. The water is drawn up into the tube because of the difference between this pressure and the atmospheric pressure. This kind of pressure, which is lower than atmospheric pressure, is called negative pressure. Next, we'll take a tube with a narrowed section and run the same experiment again, using smoke and water. You can see here that the air flows faster at the part of the tube which is narrowed. Before entering the narrowed section, the flow of air is comparatively slow. At this point, the negative pressure is weak, and the water is drawn only part way up the tube. As the air enters the narrowed section, however, it moves faster. The negative pressure increases so that more water is drawn up into the tube. The flow of air now turns the water into a spray. We call this kind of tube a Venturi tube, and the section where the tube is narrowed is the Venturi. The carburetor uses this Venturi to draw in fuel and turn it into a spray. When the piston moves downward during the engine intake process, air comes flowing into the cylinder. At this point, negative pressure is created at the Venturi so that fuel is drawn into the carburetor, turned into a spray, and mixed with the air. The carburetor has a very precise construction that lets it send just the right mixture of fuel and air to the engine under any driving conditions. There are various types of carburetors used in motorcycles. The most popular of these is the VM-type carburetor. Let's take a look at the basic construction of this type of carburetor. One of the main parts that make up the VM-type carburetor is the main bore, along which air flows when it is taken into the carburetor. Another main component is the throttle valve, which controls the amount of fuel and air by changing the diameter of the main bore. A third is the float chamber, which keeps the fuel at a constant level. Other main parts of the carburetor are the jet needle, which determines the amount of fuel and air used, the various types of jets, and the passages in which they operate. The throttle valve is joined to the throttle grip by the throttle cable. As the grip is turned, the throttle valve moves up and down. At this point, the diameter of the main bore is changed by the throttle valve, so that the Venturi goes into action. The amount of air supplied to the engine is controlled by changing the position of the throttle valve. When the throttle valve is in its lowered position, less air is supplied to the engine, and when the throttle valve rises, the amount of air increases. The throttle valve is equipped with a tapered jet needle, which is positioned inside the needle jet. As the throttle valve moves up and down, the jet needle moves up and down with it. As the jet needle moves upwards, the passage through which the fuel moves gradually grows larger, increasing the amount of fuel drawn into the engine. Thus, in the VM-type carburetor, the up and down movements of the throttle valve and jet needle are what determine the amount of fuel-air mixture supplied to the engine. In actual driving, however, in order for the carburetor to handle a wide range of driving speeds, the passages through which fuel is delivered are divided into the starter system, the pilot system, and the main system. The system that supplies fuel-air mixture to the engine at low speed is called the pilot system. In this system, both fuel passages and air passages are provided, assuring that the fuel-air mixture can be supplied to the engine even when the throttle valve is mostly closed. When the engine is rotating at low speed, for example, when it is idling, air that comes in from the pilot air passage and fuel coming in from the pilot jet is mixed and sprayed out through the pilot outlet. It is then mixed with air that has passed through the throttle valve, creating the right mixture for the engine at low speed. The pilot jet measures the amount of fuel flowing to the engine during low-speed rotation. The volume of air coming in through the pilot air passage can be adjusted by the air screw. Tightening the screw narrows the passage and reduces the amount of air coming in, so that a richer air-fuel mixture is produced. The passages that supply fuel to the engine at medium and high speeds make up what we call the main system. The main system also has two kinds of passages, those which carry fuel and those which carry air. When the throttle valve moves upward, so that the needle jet passage is opened, the venturi mixes the fuel coming in through the main jet and air coming in through the main air jet. This mixture is then sprayed from the needle jet. The amount of air mixed with the spray is determined by how far the throttle valve is open. Thus, the right mixture of air and fuel is supplied to the engine. The main jet measures the amount of fuel flowing to the engine at medium and high speeds. The main air jet measures the amount of air mixed with the fuel drawn into the carburetor. Each jet is stamped with a number indicating the size of the hole in it. A larger number indicates a larger hole diameter. At the tip of the needle, there are 5 grooves. When the clip is lowered, the jet needle is pulled upwards, so that the amount of fuel dispensed from the jet needle is increased. And this produces a richer fuel-air mixture. The carburetor also involves a number of other elements, and all of these various processes make it possible to supply the ideal fuel-air mixture to the engine to match the current driving conditions. For example, air bleeders are provided in both the main system and the pilot system, at the point where the fuel and air intersect. These air bleeders help to turn the fuel-air mixture into a spray. Let's try an experiment to see exactly how the fuel is atomized into a spray. You know that if you make holes in a straw and breathe in, both water and bubbles are drawn up the straw together. If you make the holes bigger, the bubbles get bigger too. Using this principle, we made several small holes in the side of the pilot jet, in the pilot system, and in the needle jet, in the main system. The air and fuel coming from the pilot air jet and the main air jet are mixed and bubbles are produced. This makes it easier to turn the mixture into a spray as it passes through the venturi. In order to supply a stable mixture of fuel and air to the engine, the float section is designed to make sure that the level of fuel that has accumulated in the carburetor remains constant. The float section consists of a float suspended on the fuel inside the float chamber and a needle valve which is joined to the float and moves together with it. When the fuel flows into the float chamber, the float is suspended on the fuel, and when it reaches a certain level, the needle valve closes off the entrance to the chamber so that no more fuel can come in. When the fuel level drops, the float drops also, allowing the needle valve to open so that more fuel can flow into the chamber. As the engine rotates, the float carries out this action over and over, keeping the float level at a specified position. This enables the amount of fuel sent to the venturi and the pilot outlet to be kept stable. If the float level in the carburetor should happen to drop below the specified position, the volume of fuel propelled from the venturi section decreases. If the float level is too high, however, the volume of fuel from the venturi section increases, and the engine is no longer supplied with the right mixture of fuel and air. When the engine is just being started and has not yet warmed up, it needs a richer mixture with less air in it. There has to be a way to bleed the air out and supply a richer mixture to the engine. This is done by the starter operation system, which temporarily increases the amount of fuel when the engine is started and shuts off the flow of air to make the fuel-air mixture richer. The starter system also has air and fuel passages, and the starter valve is positioned at the point where these passages intersect. When the starter valve is opened and the engine started up, the negative pressure created by the engine draws fuel through the starter jet and into the carburetor. This fuel combines with that in the pilot system to supply a richer mixture to the engine. In addition to the manual system you see here, where the starter valve is opened and closed by hand, there is also a self-starter system. The self-starter has air and fuel passages just like those in the pilot system. In this system, however, a heating element and wax are provided over the starter valve. A simplified diagram of this system would look something like this. When the engine is cold, the wax is also cold, so the starter valve is pulled upwards and a rich fuel-air mixture is sent to the engine. The engine is then started up and the current produced by the generator begins to flow to the heater, which gradually warms the wax so it begins to stretch. When this happens, the starter valve begins to shut off the passage little by little, decreasing the amount of fuel dispensed until finally, only the fuel-air mixture from the pilot system is being supplied to the engine. Up to this point, we have been talking about the basic construction and action of the VM-type carburetor. Next, let's look at what happens in the carburetor under actual driving conditions. When the engine is cold, the starter valve is activated to start the engine. If the throttle grip is opened at this point, it actually becomes harder to start the engine. This is because opening the throttle valve sharply reduces the amount of negative pressure generated by the engine, which results in less fuel being dispensed. It also allows a larger volume of air to be taken in, causing the fuel-air mixture to be leaner. Next, let's look at what happens to the carburetor when the engine is started and warmed up and reaches the idling speed. When the engine is idling, the amount of air determined by the air screw is mixed with the volume of fuel measured by the pilot jet and passes through the pilot outlet. At this point, the mixture is turned into a spray by the air coming under the throttle valve. Because of this, turning the air screw changes the amount of air taken into the pilot system, and this changes the fuel-air ratio, which in turn changes the idling speed. Turning the throttle stop screw, on the other hand, causes the throttle valve to move up and down, and this changes the amount of fuel-air mixture sent to the engine, thus changing the engine speed. Therefore, both of these screws are turned to adjust the idling speed so that the right mixture of air and fuel can be obtained. If the throttle grip is turned a little to boost the speed from idling to the low speed range, the throttle valve is pulled upwards slightly. This causes the jet needle to be pulled upwards also, so that fuel from the main system is added to that already coming in from the pilot system. At the same time, the amount of fuel-air mixture flowing to the engine increases, and this boosts the engine speed. If the throttle grip is turned further, we reach the middle and high speed ranges, and the throttle valve is pulled upwards even further. The negative pressure near the pilot outlet drops, so less fuel comes from the pilot system. More fuel comes from the main system, however, and more air from the main bore, so that a large volume of fuel-air mixture reaches the engine, boosting the power. What enables the motorcycle to start moving is the power produced by the engine being conveyed to the drive wheels. This is why we call the overall system by which this power is conveyed the powertrain. The powertrain consists of the primary reduction system, the clutch, the transmission, and the final reduction system. The reciprocal action of the pistons can be changed by using the crankshaft to change the rotating movement. The primary reduction system then reduces the speed at which the crankshaft turns, thus increasing the torque, and transmits the power to the clutch. The power transmitted to the clutch is changed by the transmission into speed and torque in response to driving conditions. The final reduction system then reduces the speed further so that the power is conveyed to the drive wheel. Let's take a closer look at each of these transfer systems. The primary reduction system is a mechanism located between the crankshaft and the transmission. In a motorcycle, primary speed reduction is ordinarily carried out by a primary drive gear attached to the crankshaft and the clutch housing, which is a primary driven gear. The speed reduction ratio is set anywhere between 1.5 to 1 and 4 to 1. In other words, the clutch housing rotates one time every time the crankshaft turns from 1.5 to 4 times, so that the countershaft of the transmission, which is connected directly to the clutch, rotates once. The crankshaft speed can reach as high as 10,000 revolutions per minute. By providing this primary reduction system, however, the speed at which the countershaft rotates can be suppressed even when the engine is running at high speed. And this keeps the inertial force on the gear itself low. When the clutch is disengaged, the gear rotation slows promptly, so that gears are changed smoothly. In order for a motorcycle to start up smoothly, the power must be conveyed to the wheels gradually, instead of all at once. And once this power has been conveyed, it must drive the wheels smoothly and continuously without letting them slip. Also, when the transmission changes gears, it is difficult to shift smoothly from one gear to another unless we temporarily cut off this flow of power from the engine. The clutch is what enables this flow of power from the engine to be conveyed or cut off as necessary. The ordinary motorcycle uses a type of clutch called a friction clutch. The friction clutch uses the friction force between the drive plate on the engine side and the driven plate on the transmission side to convey or cut off the power from the engine. There are two types of friction clutch. The dry type uses air to cool the friction heat produced when power is conveyed, and the wet type clutch, which uses oil for cooling. Each type can either be a single plate type, which has only one friction plate, or a multi-plate type, which has a number of friction plates. Most motorcycles use the wet type multi-plate clutch. In this clutch, drive plates and driven plates are stacked alternately and are pushed by springs to convey power. All of the parts in this type of clutch are lubricated by oil. In order to understand the basic operation of this clutch, let's look at how the various components are connected. First of all, the clutch housing is mounted on the countershaft, but it is not connected to the countershaft, allowing the shaft to rotate freely. The clutch sleeve hub is coupled to the countershaft by means of a spline, so it rotates together with the countershaft. The drive plates and driven plates are stacked alternately, but the drive plates are connected to the clutch housing side and the driven plates are connected to the clutch sleeve hub side. This pressure plate is pushed against the drive plates and driven plates by means of spring force. Because the drive plates and driven plates are being pressed against by the springs, they rotate along with the clutch housing when it rotates, thus turning the countershaft. In this way, the power from the engine is transmitted from the crankshaft to the clutch housing, and the friction force generated by the drive plates and driven plates is conveyed from the clutch sleeve hub to the transmission. There are two methods used to move the pressure plates. In one, the rack and pinion system, a pinion installed on the clutch release shaft pulls on the clutch release rack, forcing the spring to compress. In the other, the push rod type, the plate is pressed from the opposite direction by a push rod to compress the spring. When the spring is compressed, a gap is created between the clutch drive plates and the driven plates, so that no power is conveyed to the clutch sleeve hub, even when the clutch housing rotates. Therefore, no power is transmitted to the countershaft either. The capacity of the clutch is proportional to the number of clutch plates and the size of the surface area where friction is generated, as well as to the strength of the clutch spring. The clutch is provided with damper springs and damper rubbers which absorb the impact caused by changes in torque from the crankshaft and drive wheels and allow the force to be transmitted smoothly. Another type of clutch is the automatic centrifugal type clutch, used in some motorcycles with lower displacement. With this automatic centrifugal clutch, the clutch is disengaged when the engine is at idling or near idle speed and is automatically engaged when the engine speed increases. There are also motorcycles which use this type of clutch. In this type, the frictional force of the clutch shoe and the clutch drum is used to transmit drive power from the crankshaft to the transmission and to cut off this power when necessary. This clutch shoe is connected to the crankshaft. The clutch drum is connected to the primary drive gear. The primary drive gear is connected to the primary driven gear, which is consolidated with the gear shifting clutch. The gear shifting clutch, in turn, is connected to the countershaft by means of a spline coupling and conveys the drive power to the transmission. The clutch weight is what pushes the clutch shoe and the clutch drum together automatically. The action of this weight utilizes the centrifugal force produced when the engine rotates. At low speed, less centrifugal force is acting on the weight. The clutch shoe is pulled inwards by the elasticity of the spring and no power is transmitted. As the engine speed increases, so does the centrifugal force. Now the clutch shoe widens outwards because of the elasticity of the spring and compresses the clutch drum, so that the drive power is carried to the transmission. In this way, the clutch uses the changes in the engine speed to transmit drive power at the appropriate time. Also, with this clutch, there is less shock produced when the gear shifting lever is operated. And this means that the gear shifting clutch can be used for smoother shifting from one gear to another. The transmission is what changes the torque and speed of the engine so that the motive power, which has undergone primary speed reduction, is appropriate to the current driving conditions. Let's look at how the transmission works using computer graphics to simulate the operation. You know that starting the engine and climbing uphill both require a high level of power. In situations like these, the number of teeth on gear A on the drive side is reduced, and the number of teeth on gear B on the driven side is increased. You can see that gear B is rotating at a slower speed than gear A. Let's talk here about why changing the number of teeth on the gears changes the torque. When the gear is rotating, because to every action there is an equal and opposite reaction, for a force acting at the contact point, there will be an equal and opposite force F. At this point, if we use a wrench and turn the bolts at the centers of the gears, assuming the torque is being applied, we can express the rotational torque TA of gear A as an equation showing that a force F is applied at the contact point of the radius RA of the gear. In the same way, the torque TB of gear B can be expressed using an equation like that shown here, with the radius of gear B being twice as large as that of gear A. Therefore, when the number of teeth on gear B is twice that on gear A, the level of torque is twice as high. Conversely, at high speeds, when we do not need a large amount of torque and the rotation speed of the drive wheels is increased, we increase the number of teeth on gear A on the drive side and reduce the number of teeth on gear B on the driven side. You can see that gear B is now rotating faster than gear A. In this way, by changing the speed at which gear A and gear B rotate, or in other words, by changing the number of teeth on the gears, we can produce a torque and speed that are appropriate to the driving conditions. The ratio of the speed of gear A to that of gear B, in this case, is called the gear ratio. If the torque is doubled, the speed is reduced by half, and the amount of work produced per minute, namely the horsepower, remains the same. In an actual transmission, there are a number of stages provided between the gear which affords the maximum climbing power and the gear which provides the maximum speed. This way, the appropriate gear ratio for the current driving conditions can be selected. The transmission system is made up of the counter shaft, which served as the input axis, the drive shaft, which acts as an output axis, the various gears which convey the drive power to the engine, and the gear shifting cam and gear shifting fork, which are used to operate the gears. This type of transmission is called a constant mesh transmission, because the gears on the counter shaft are meshed with the gears on the drive shaft right from the start, and remain meshed, rotating together. At any given time, however, either the counter shaft gear or the various gears on the drive shaft are not coupled to the shaft. In neutral gear, therefore, the power from the counter shaft is not transmitted to the drive shaft. Let's look at how power is transmitted when we shift from neutral into low gear. In neutral gear, the low gear of the countershaft is consolidated with the shaft to form a single unit. But the low gear of the drive shaft is free. When the gear shifting lever is operated, the gear shifting cam rotates and the gear shifting fork slides to the dog, so that the dog is fitted onto the low gear of the drive shaft. Because the dog is coupled with the drive shaft, power is transmitted from the countershaft to the drive shaft. As the rider shifts through various gears from low to top gear, the gear shifting cam and gear shifting fork work together to change from one speed to the next. There is also a type of automatic transmission which uses a V-belt. This gear-changing mechanism consists of a drive pulley, a driven pulley, a drive belt, and a centrifugal clutch built into the driven pulley. In order for a motorcycle to start up smoothly, the power must be conveyed to the wheels gradually, instead of all at once. And once this power has been conveyed, it must drive the wheels smoothly and continuously without letting them slip. Also, when the transmission changes gears, it is difficult to shift smoothly from one gear to another unless we temporarily cut off this flow of power from the engine. The clutch is what enables this flow of power from the engine to be conveyed or cut off as necessary. The ordinary motorcycle uses a type of clutch called a friction clutch. The friction clutch uses the friction force between the drive plate on the engine side and the driven plate on the transmission side to convey or cut off the power from the engine. There are two types of friction clutch. The dry type uses air to cool the friction heat produced when power is conveyed, and the wet type clutch, which uses oil for cooling. Each type can either be a single plate type, which has only one friction plate, or a multi-plate type, which has a number of friction plates. Most motorcycles use the wet type multi-plate clutch. In this clutch, drive plates and driven plates are stacked alternately and are pushed by springs to convey power. All of the parts in this type of clutch are lubricated by oil. In order to understand the basic operation of this clutch, let's look at how the various components are connected. First of all, the clutch housing is mounted on the countershaft, but it is not connected to the countershaft, allowing the shaft to rotate freely. The clutch sleeve hub is coupled to the countershaft by means of a spline, so it rotates together with the countershaft. The drive plates and driven plates are stacked alternately, but the drive plates are connected to the clutch housing side, and the driven plates are connected to the clutch sleeve hub side. This pressure plate is pushed against the drive plates and driven plates by means of spring force. Because the drive plates and driven plates are being pressed against by the springs, they rotate along with the clutch housing when it rotates, thus turning the countershaft. In this way, the power from the engine is transmitted from the crankshaft to the clutch housing, and the friction force generated by the drive plates and driven plates is conveyed from the clutch sleeve hub to the transmission. There are two methods used to move the pressure plates. In one, the rack and pinion system, a pinion installed on the clutch release shaft pulls on the clutch release rack, forcing the spring to compress. In the other, the push rod type, the plate is pressed from the opposite direction by a push rod to compress the spring. When the spring is compressed, a gap is created between the clutch drive plates and the driven plates, so that no power is conveyed to the clutch sleeve hub, even when the clutch housing rotates. Therefore, no power is transmitted to the counter shaft either. The capacity of the clutch is proportional to the number of clutch plates and the size of the surface area where friction is generated, as well as to the strength of the clutch spring. The clutch is provided with damper springs and damper rubbers which absorb the impact caused by changes in torque from the crankshaft and drive wheel and allow the force to be transmitted smoothly. Another type of clutch is the automatic centrifugal type clutch, used in some motorcycles with lower displacement. With this automatic centrifugal clutch, the clutch is disengaged when the engine is at idling or near idle speed and is automatically engaged when the engine speed increases. There are also motorcycles which use this type of clutch. In this type, the frictional force of the clutch shoe and the clutch drum is used to transmit drive power from the crankshaft to the transmission and to cut off this power when necessary. This clutch shoe is connected to the crankshaft. The clutch drum is connected to the primary drive gear. The primary drive gear is connected to the primary driven gear, which is consolidated with the gear shifting clutch. The gear shifting clutch, in turn, is connected to the countershaft by means of a spline coupling and conveys the drive